This chapter will be developed in more detail, keeping the book format in Malay, covering Ramanujan's taxi numbers, Kaprekar's constant, Pythagorean triangles, and the Fibonacci sequence with the golden ratio. It also adds new examples, detailed calculations, deeper mathematical connections, and applications in the Malaysian context on October 7, 2025 at 1:45 p.m. Malaysian time. Practical activities, additional Python code, and advanced explorations such as connections to modern number theory and local culture are also included. Repetition of previous examples is avoided, and the content remains concise but comprehensive. If M refers to something specific, please state it. Charts are limited unless requested, and confirmation will be requested if images are needed according to guidelines. On October 7, 2025, at 1:45 p.m. in Malaysia, as monsoon winds caress the rice fields in Perlis and neon lights illuminate Dataran Merdeka, we are surrounded by invisible mathematics. Numbers are not just tools for calculation, but secrets that organize the universe. From the spirals of orchid petals in the Perdana Botanical Garden to the algorithms that power delivery drones in Cyberjaya. In this chapter, we delve into the discoveries of four mathematical geniuses. Srinivasa Ramanujan with his symmetrical taxi numbers, Dr. Kaprekar with his fascinating constant, Pythagoras with his harmonious triangles, and Fibonacci with the sequence that leads to the golden ratio. Through modular arithmetic, we uncover the patterns of taxi numbers. Through the golden ratio, we see the beauty of nature. Each section is accompanied by how, calculation methods and experiments, and why, importance in science, technology, and Malaysian culture in 2025. With Python code and practical challenges, this chapter invites you to explore the mathematical secrets of the universe, from classrooms in Johor to AI servers in Selangor. A taxi number is a positive whole number that can be expressed as the sum of two cubes in at least two different ways. For example, the fifth taxi number, 87,539,319, has pairs. 167 cubed plus 436 cubed equals 4,657,463 plus 82,881,856 equals 87,539,319. 228 cubed plus 423 cubed equals 11,852,352 plus 75,686,967 equals 87,539,319. Modular arithmetic helps understand taxi numbers through their remainders when divided by 9, because cubes only produce remainders of 0, 1, or 8 modulo 9. An example of a new taxi number, 9,926,315. Pairs, 99 cubed plus 116 cubed equals 970,000, 299 plus 1,620,896 equals 9,926,315. 103 cubed plus 114 cubed equals 1,092,727 plus 8,832,114 equals 9,926,315. Digital root, 9 plus 9 plus 2 plus 6 plus 3 plus 1 plus 5 equals 35, 3 plus 5 equals 8. Remainder modulo 9. Advanced exploration. Taxi numbers can be tracked using the sum of digital roots of cube pairs. For 9,926,315, the pairs 99, 116 and 103, 114 show consistent remainders with modular properties. Contextual example. Take the number 7,102,025, the date October 7, 2025. Activity. Find the next smallest taxi number after 9,926,315 using Python code. Taxi numbers reveal a rare symmetry in number theory as they require multiple pairs of cubes to lead to the same number. Their modular properties, remainders of 0, 1, 2, 7, or 8, modulo 9, indicate a mathematical preference that resembles patterns in quantum physics or modern algorithms. In 2025, taxi numbers are relevant in algorithms based on modular remainders, e.g., RSA, protecting e-commerce transactions on Shopee Malaysia, error detection in databases using remainders modulo 9, such as in smart traffic management systems in Kuala Lumpur. These special numbers reflect the concept of balance in Malay philosophy, like harmony in Zapin dance. Calculate the digital root of the taxi number 151,875. Test your favorite number. 25,102,025. Deepavali Day 2025. Is it a taxi number? The golden ratio, phi, which is about 1.6180339887499895, is the limit of the ratio of two consecutive Fibonacci numbers 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. It is also the solution to the quadratic equation x squared minus x minus 1 equals 0, which is x equals 1 plus the square root of 5 divided by 2. Ratio calculation. F20 equals 6,765, F19 equals 4,181. Ratio 6,765 divided by 4,181 is approximately 1.6180333963. For larger numbers, such as F40 equals 102,334,155, F39 equals 63,245,986, the ratio is more precise. 102,334,155 divided by 63,245,986 is approximately 1.618033398875. Algebra. Solve x equals 1 plus 1 divided by x. So x squared equals x plus 1. So x squared minus x minus 1 equals 0. Roots. X equals 1 plus or minus the square root of 5 divided by 2. Phi equals 1 plus the square root of 5 divided by 2 is approximately 1.618. In nature, lotus flowers in Titiwangsa Lake on October 7th, 2025. The number of seed spirals often follows Fibonacci numbers, e.g. 34 or 55. The ratio of distances between spirals is approximately phi to maximize light exposure. Advanced exploration. The Fibonacci sequence is related to continued fractions. Phi equals 1 plus 1 divided by 1 plus 1 divided by 1 plus. This quickly approximates phi. 1 plus 1 divided by 1 equals 2. 1 plus 1 divided by 1 plus 1 divided by 1 equals 3 divided by 2 equals 1.5. 1 plus 1 divided by 1 plus 1 divided by 1 plus 1 divided by 1 equals 5 divided by 3 is approximately 1.666 and so on. Python code to calculate ratios and sequences. The golden ratio creates visual harmony and structural efficiency, appearing in various fields in 2025. The spirals of orchid or lotus flowers in Malaysia follow phi for optimal seed distribution. New buildings in Putrajaya, such as the 2025 Innovation Center, use phi in window and facade ratios for aesthetics and energy efficiency. Fibonacci search algorithms are used in AI for traffic data analysis on smart highways in Malaysia. Exclusive Deepavali 2025. Batik patterns in Malacca use golden spirals for captivating traditional designs. Phi-based quasi-crystal structures in nanomaterials improve the efficiency of solar panels in Sabah. The golden ratio connects mathematics with beauty, making it the signature of the universe. Calculate the ratio of 2,584 divided by 1,597 and compare it to phi. Find Fibonacci patterns in local plants, e.g., hibiscus petals in community gardens. Kaprekar's constant, 6,174, is the fixed point for a 4-digit number, Digits not all the same. When you arrange the digits from largest to smallest, subtract the number from smallest to largest, and repeat the process until you reach 6,174. Try a new number, 7,502. Step 1. 7,520 minus 257 equals 7,263. Step 2. 7,632 minus 2,367 equals 5,265. Step 3. 6,552 minus 2,556 equals 3,996. Step 4. 9,963 minus 3,699 equals 6,264. Step 5. 6,642 minus 2,466 equals 4,176. Step 6. 7,641 minus 1,467 equals 6,174. Digital root. 7,502. 7 plus 5 plus 0 plus 2 equals 14. 1 plus 4 equals 5. 6,174. 6 plus 1 plus 7 plus 4 equals 18. 1 plus 8 equals 9. Most numbers converge in 7 steps, with the digital root of 6,174 always being 9, equivalent to 0 modulo 9. Contextual example. Take the number 0745, time 1:45 p.m., October 7 written as 4 digits. Advanced exploration. The Kaprekar process is a discrete dynamic system, similar to fixed points in physics, e.g. thermodynamic equilibrium. 3-digit numbers converge to 495. Python code. Kaprekar's constant acts like a mathematical black hole, pulling other numbers to the fixed point of 6,174. This reflects stability in dynamic systems, like weather cycles in Malaysia. In 2025, this pattern inspires optimization algorithms in AI for weather forecasting in the Klang Valley. The Kaprekar process is used in STEM activities in Malaysian schools to teach logic and patterns. This concept of balance parallels Malay philosophy about harmony in the community. Test the Kaprekar process with 5,123. How many steps to 6,174? Try a 3-digit number, e.g. 725, and find the constant 495. A right-angled triangle with whole number sides, 20, 21, 29, satisfies 20 squared plus 21 squared equals 29 squared. New example, 20, 21, 29. Test, 20, 21, 29. Method. Find 3 whole numbers using Euclid's formula. M squared minus n squared, 2mn. M squared plus n squared. M is greater than n is greater than 0. For example, m equals 5, n equals 2. Contextual example. Measure a window frame in your house on October 7, 2025. If the sides are approximately 60 centimeters, 80 centimeters, 100 centimeters, it is a 3, 4, 5 triangle times 20. Advanced exploration. The digital root of squares maintains modular properties. A squared plus b squared is congruent to c squared modulo 9. This connects geometry with number theory. Python code to generate Pythagorean triangles. Pythagorean triangles connect geometry with number theory, showing harmony between shapes and numbers. In 2025. Used in bridge construction in Sarawak, ensuring structural stability. Molecular structures of crystals in nanotechnology follow Pythagorean ratios. These triangles symbolize balance in traditional Malay architecture, such as longhouses. Verify the triangle 12, 35, 37 and calculate the digital root. Find Pythagorean triangles in everyday objects, e.g. school door frames. On October 7, 2025, at 1:45 p.m. in Malaysia, we have explored the mathematical secrets of the universe through Ramanujan's taxi numbers, Kaprekar's constant, Pythagorean triangles, and Fibonacci's golden ratio. Modular arithmetic reveals the symmetry of numbers, while the golden ratio shows the harmony of nature and design. These patterns form technology, e.g., smart traffic AI in Johor, nature, e.g., lotus spirals in Perak, and culture, e.g., Deepavali 2025 Batik in Melaka. Continue your adventure. Calculate numbers, observe patterns around you, or write code to discover new secrets. The universe is a mathematical canvas, and you are its explorer. 1. Calculate the digital root of the taxi number 20,683. 2. Find the golden ratio in batik patterns or local architecture. 3. Test the Kaprekar process with 9012. 4. Find Pythagorean triangles in household furniture. It's 1:45 p.m. in Kuala Lumpur. From this high window, we can see the whole city that never sleeps, where every moment is full of movement and activity. The hot sun shines on the skyscrapers, and below, thousands of people go about their daily routines. This city pulses with life. Endless traffic jams, towering skyscrapers, and crowds always moving to their destinations. Every street is filled with all sorts of people, from students to workers, all part of the city's heartbeat. In every corner, there's a story, movement, and a unique rhythm. But behind all this hustle and bustle, there's a secret language hidden: mathematics. It's not just a school subject, but the foundation of everything we see and experience in this city. Every building, every movement, and every pattern on the streets is actually shaped by unseen numbers and equations. From the design of the iconic Petronas Twin Towers, built on Islamic geometric principles, to the digital signals that connect the whole city, numbers shape everything. Modern technology, traffic lights, and even digital billboards all work with the help of complex math. Every inch of this city is the result of human calculation and creativity. Today, we're going to uncover Malaysia's secret patterns, the mysterious Ramanujan taxicab numbers, the Fibonacci spiral that shows up in nature and architecture, the unique Kaprekar constant, and the wisdom of Pythagoras that has shaped the modern world. Each one has its own story hidden behind our daily lives. This isn't just for mathematicians, it's for anyone who wants to know more about the world around them. Whether you're a student, a worker, or a tourist, the beauty of math can be found everywhere if you know where to look. It's a universal language that connects us all, no matter our background or age. Let's look past the ordinary and find the elegant equations that bring everything together, starting with a short story about a taxi. On this journey, we'll see how numbers and patterns are hidden in every part of life in Kuala Lumpur, and how they shape our everyday experiences. Get ready to see this city with new eyes, through the amazing lens of mathematics. Our journey starts with something that seems very ordinary, a taxi number. But hidden behind this number is an amazing math story, made famous by the well-known mathematician Ramanujan. In Malaysia, every taxi has a special number. But have you ever thought that these numbers could mean something deeper? Let's dive into the story behind these seemingly plain numbers. 1729 isn't just any number. It's the smallest number that can be written as the sum of two cubes in two different ways: 13 plus 123 and 93 plus 103. This story began when Ramanujan, talking with G.H. Hardy, realized how special this number was. In Malaysia, we might see this number on the streets, on taxi plates, or even on signs, without knowing how unique it is. Now imagine we fast forward to modern Kuala Lumpur. A young programmer in Cyberjaya gets project ID 4104. By chance, this is also a special taxi number. This number isn't just random. It carries the same math history as 1729, connecting the past and future through the digital world and new ideas. 4104 also has its own special quality. 4104 equals 23 plus 163 equals 93 plus 153. Two different ways to get the same answer, showing the hidden beauty in math. Every number tells a story, and sometimes that story is waiting to be found by those who are curious enough to look for it. Numbers like 1729 and 4104 aren't just accidents. They are math treasures hidden all around us, waiting to be found by anyone who dares to ask questions and explore. In libraries, in offices, or on the streets. The magic of math is always around us. You can even try it yourself. Calculate both combinations for 1729 and 4104 and see the magic of math happen right before your eyes. This process not only sharpens your mind, but also opens your eyes to the beauty of logic and creativity in math. Or, if you're into technology, try writing a simple Python script to find more taxicab numbers. This is a modern exploration driven by curiosity, mixing the world of classic math with today's tech advancements. Every line of code brings you closer to new discoveries. Remember, the real fun is in the journey of discovery itself, not just in the final answer. In a world that's always changing, curiosity and a spirit of exploration will always lead us to amazing discoveries. Keep looking, because every number might hold an incredible story. Are taxicab numbers just a strange thing? Not at all. Number theory, once thought of as useless, now keeps our digital world safe, our banking, messaging, and so much more. Encryption relies on math problems that are easy to do one way, but almost impossible to undo. As quantum computing gets better, new ways of keeping things secret will depend on even deeper number theory. Ramanujan's curiosity now helps protect your e-wallet and your online life. The journey from abstract math to real-world safety proves no knowledge is ever wasted. Let's step into the Malaysian rainforest, where the magic of math is hidden behind the lush greenery. Here, under the thick canopy and among the dense leaves, the Fibonacci sequence isn't just a theory, it's the heartbeat of life. Every step brings us closer to nature's secrets that have been around for millions of years, shaping a rich and diverse ecosystem. Here, 1, 1, 2, 3, 5, 8. This is the Fibonacci sequence, where each number is the sum of the two numbers before it. This sequence isn't just numbers, it's a secret code that nature uses to arrange growth and shapes. Look at how fern leaves slowly uncurl, or how new shoots grow in the same pattern, making sure every leaf gets enough light and space to thrive. From this sequence, the golden ratio is born, about 1.618, which is the base for many beautiful shapes in nature. This ratio forms flower petals, snail shells, and the spirals we see in plants and animals. Every spiral and pattern created is not only beautiful to look at, but also helps plants and animals live more efficiently. The hibiscus flower, a symbol of Malaysian pride, follows this math plan in how its petals are arranged. Sunflower seeds are arranged in Fibonacci spirals, making the most of space and light. The nautilus shell grows in a golden spiral, allowing the animal to grow without changing its basic shape. Each one is proof of nature's amazing design based on math. Nature uses the Fibonacci sequence not just for beauty, but also for survival. These patterns help flowers attract pollinating insects, making sure seeds are spread more widely. Birds and insects also rely on these arrangements to find food and shelter. Every creature benefits from this mathematical master plan. Next time you walk in a park or forest, try to notice the flower petals, the arrangement of leaves, or the spirals on a shell. Count the petals, trace the spirals. You'll find the Fibonacci sequence hidden everywhere, waiting to be discovered by a keen eye. Or, if you like technology, try coding the sequence yourself. See how the golden ratio appears in graphs and digital patterns, connecting the natural world with the modern world. The same math that shapes the rainforest also shapes our architecture, music, and technology today. This is the beauty of simple math, a universal design that connects all life on Earth. From the Malaysian rainforest to the digital world, the Fibonacci sequence proves that nature is always thinking mathematically. The golden ratio isn't just in nature, it's also in Malaysian art and buildings. The Iron Mosque in Putrajaya, Songket weaving, and even the curve of a keris blade all show these balanced proportions. Artists and architects naturally use these patterns for balance and beauty. Try drawing a golden rectangle over your favorite building or design a logo using that ratio. The result? A natural balance, ancient math in a modern look. The golden ratio connects old traditions with new ideas. Meet Kaprekar's constant, 6174, the mathematical black hole. Pick any 4-digit number, not all digits the same, rearrange it to make the biggest and smallest numbers, subtract and repeat. In just a few steps, you'll always land on 6174. This fun routine teaches logic and programming, perfect for Malaysian classrooms and coding boot camps. Try it with your birth year or phone number digits, or automate it with a Python script and watch the magic happen. Kaprekar's constant is a puzzle, a lesson, and a gateway to algorithmic thinking. Math can be mysterious and fun. The Pythagorean theorem, A2 plus B2 equals C2, is the backbone of our world. Every building, road, and even your phone's GPS relies on right angles and triangles. Builders use it to make sure angles are perfect. GPS satellites use it to pinpoint your location. Try measuring your phone's width and height, then figure out the diagonal with the Pythagorean formula. Or code a quick calculator to see it in action. This old principle is everywhere, from construction sites to navigation apps. Geometry is the hidden structure of modern life. Pythagoras' legacy runs deep in Malaysia. Ancient temples in Lembah Bujang, traditional kites, and even video game graphics all rely on the rules of geometry. Builders and skilled craftspeople mastered these ideas long before they were written down as formulas. Today, that same math powers 3D graphics and game engines in Malaysia's tech industry. From old stones to the digital world, simple geometry connects us all. The power of math is timeless. It brings together the past, present, and future. As the sun sets over Kuala Lumpur, our math journey comes to an end. But your adventure is just beginning. We've seen how numbers shape nature, art, technology, and everyday life. Math isn't just for textbooks. It's a tool for exploring, asking questions, and creating. Try counting petals, measuring things, or coding new patterns. Ask, what if, and follow where your curiosity takes you. The universe is full of puzzles waiting for you to solve. Your math journey starts now.